Okay, welcome back to AI Paper Podcasts. Let's unpack this. We are diving into a really significant paper today, Scaling Agents via Continual Pre-training. It's from Tanguy Lab at Alibaba Group, and it details their AgentFounder 30B model.
Yeah, this one's quite impactful. Our mission for this session is really to shortcut you straight to the core idea here, because it represents a pretty fundamental shift in how we might build high-performance AI agents going forward.
And that core idea, it's actually simple, but wow, is it critical. It tackles why current large language models, especially the open source ones, often, stumble when they face complex multi-step tasks as agents.
Right. The paper calls it the dual burden, and it boils down to an optimization conflict, basically.
Think about it, right? The standard ways we train agents after initial pre-training, supervised fine-tuning, SFT, reinforcement learning, RL, they force this general-purpose foundation model to learn two massive kind of conflicting things simultaneously.
Exactly. First, it has to pick up the basic foundational capabilities of being an agent, like how do we even call a tool? How do I structure multi-step reasoning?
And then at the same time, it's supposed to perfectly align those brand new, maybe shaky skills to expert demonstrations.
It just creates this incredible tension. The paper's analogy isn't quite this, but it's like trying to install the core operating system on a computer while also trying to run, complex video editing software on it. Things are bound to clash.
The system just crashes, metaphorically speaking. So their key insight, the big solution they propose, is adding this crucial intermediate step, Agentic Continual Pre-training or Agentic CPT.
Yeah, this is the core. It's essentially like flashing some agent-specific firmware onto the base model first. It creates what they call a pre-aligned agentic foundation. So the model already understands things like tool use and planning before you even start the usual fine-tuning process.
And the results, the proof is in the pudding, as they say. This AgentFounder 30B model hits state-of-the-art across 10 different benchmarks.
And notably, it became the first open-source model to crack the 30-point barrier on humanity's last exam, HLE, which is a notoriously difficult research benchmark. They hit 31.5% pass at 1.
That is genuinely huge for the open source community.
Definitely. And it also got 72.8% on the GIA text benchmark, 39.9% on BrowseCompare, often beating sophisticated closed-source research agents. It really signals that this Agentic CPT could be, maybe is, the necessary foundation layer we've been missing for truly capable agents.
Okay, so let's dig into that foundation. They start by redefining alignment itself, moving from what we normally think of static alignment to agentic alignment.
Right. We're used to think about alignment as, does the model's final output match human preferences or instructions? Static.
But agentic alignment is dynamic. What does that mean in practice?
It means the model needs to maintain behavioral consistency while operating in a dynamic, unpredictable environment. It's not just about the final answer being right.
It's about the whole process. Like, can it keep a coherent reasoning chain going? Can it handle a tool failing mid-task?
Exactly. Or what if the information it gets early on turns out to be misleading? Can it adapt? That's agentic alignment.
That sounds like a massively larger, more complex space to align within. And the paper points out, if you try to do this only with supervised fine-tuning, you hit a major bottleneck.
Yeah, the data problem. You'd need an impossibly huge data set of complete, high-quality, long-horizon trajectories covering every possible scenario. It's just not feasible.
Right. You can't possibly demonstrate every way a task could go wrong or need adaptation.
And even with the limited trajectory data we do have, SFT tends to lock the model into just imitating those specific paths it saw.
So it learns to mimic one sequence perfectly, but it loses the ability to be flexible, to make its own good decisions when things go off script.
Precisely. It doesn't foster that flexible decision-making you need. The paper argues general foundation models lack the right agentic inductive biases. They aren't inherently built to think in terms of planning, tools, and dynamic adaptation.
And that's the gap CPT is designed to fill. It installs those biases, that foundational understanding, before the fine-tuning stage.
So the later SFT or RL can just focus on high-level alignment with expert strategy, not teaching the absolute basics of tool use from scratch. It resolves that dual burden.
Okay, so how did they actually implement this Agentic CPT? Walk us through the pipeline.
So it's right in the middle. You have your initial base model. Pre-training, they use the Quen series models from Alibaba. Then comes Agentic CPT. And then comes the final post-training, like SFT or RL.
It's a dedicated middle layer. And they had some strong principles about the data used for CPT, right?
Yeah, two key things. One, the data has to be broad and diverse, covering lots of domains so the skills are transferable. You You don't want an agent that only knows one specific task.
Makes sense. Avoid overfitting to a narrow domain.
And two, the data needs to comprehensively cover various types of agentic behaviors: planning, tool use, reasoning, error handling. This is to prevent the model from just memorizing specific sequences again. It needs to understand the patterns of agency.
Okay, and dealing with that amount of diverse data must be challenging. How did they structure the training?
They used a pretty clever two-stage progressive strategy. Stage 1 uses a hefty chunk of data, about 200 billion tokens. This is mostly what they call first-order action synthesis, or FAS data, which we'll get into.
And that's trained within a standard context window.
Right, a 32K context window for Stage 1. The focus here is just preliminary acquisition, getting the model familiar with basic tool invocation patterns and multi-step reasoning structures, kind of like learning the alphabet and basic grammar of agency.
Okay, the initial grounding. What happens in Stage 2?
Stage 2 gets more sophisticated. You use about 100 billion tokens, but this time it's curated, higher quality data, what they call high-order action synthesis, or HASE data.
And the big change here is
the context window. They jump to an extended 128K context window in Stage 2.
Whoa, okay. Why such a huge leap in context size for the second stage?
Because complex agentic behavior, especially things like research tasks or deep problem solving, requires long horizon planning. If a task takes, say, 30 steps involving multiple tool calls and reasoning adjustments, the model needs a massive working memory to keep track of everything.
Right, the entire history needs to fit for the model to make informed decisions later on.
Exactly. So Stage 2, with that 128K context, specifically focuses on teaching those sophisticated long-horizon planning strategies and understanding complex action spaces. That's where the really deep agentic capabilities are honed.
This brings us neatly to the data generation itself. You mentioned FAS and ACS. Let's start with FAS, first-order action synthesis. This seemed like a really core innovation for making this scalable.
Absolutely. The challenge is always cost and scale, right? Getting enough high-quality agent training data usually involves tons of real-world interactions, maybe expensive API calls like Google Search or specific data providers.
Which gets astronomically expensive very quickly if you need billions of tokens.
Precisely. So FAS is designed to generate vast amounts of agentic training data offline without needing any external tool calls during the generation process itself.
Okay, how do they create realistic agent-like data without actually running the agent?
It's a two-phase process. Phase 1 is about building a knowledge base. They take unstructured text web crawls, historical tool responses they might have, documentation, and transform it into something structured they call entity-anchored open-world knowledge memory.
Entity-anchored. Okay, how's that different from, say, a standard knowledge graph?
It's denser and context-rich. Instead of just linking Paris to France, they anchor specific declarative statements to the entity Paris. For example, a statement about museum visitor numbers from a specific source on a specific date, or a snippet about transit policy changes. It preserves crucial context, like time and source.
Got it. So you have these rich, context-aware knowledge snippets linked to entities. What's phase 2?
Phase 2 is the question synthesis engine. They sample clusters of these related entities and automatically generate diverse questions that require synthesizing information from those different knowledge points.
Ah, so they deliberately create questions that you probably couldn't answer just from one document, forcing the need for multi-hop reasoning or simulated tool use.
Exactly. The paper gives a great example using Paris. They combine knowledge about a specific museum, a citywide transit issue, and maybe an upcoming event, and synthesize a complex question that, if a human were answering it, they'd almost certainly need to use search tools or look things up.
Okay, so they've generated complex questions grounded in real-world knowledge snippets. How does FAS turn that into agentic training data, like plans and actions?
It has two main synthesis components. First is planning action synthesis. For a single complex question, they generate multiple, say, K, different reasoning and action perspectives, different potential plans or ways to approach solving it.
So for one question, the model sees several plausible ways an agent might think about tackling it. That expands the training signal massively.
Right. Instead of one perfect trajectory, it sees a diverse set of reasonable approaches. But you raise a good point. How do you ensure these synthesized plans aren't just, well, garbage?
Yeah, K different plans sounds like a recipe for a lot of noise.
They use quality control. It's called reject sampling based on knowledge alignment verification. Essentially, they use another LLM as a judge.
An LLM judging LLM outputs.
Right. This judge estimates the probability that a synthesized plan or action sequence would actually lead to acquiring the necessary knowledge if it were executed. Plans with a low probability are just filtered out.
Clever. So they filter before execution, saving all that potential cost, and focusing the training data on promising paths. That's the efficiency gain.
That's a big part of it. The second component is reasoning action synthesis, which focuses on logical deduction after information might have been hypothetically acquired.
So this is more about the internal thought process.
Yeah. It uses a two-step scheme. Step 1. Decompose the question and generate an initial speculative answer, A1. Step 2. Refine that speculation, A1, using the relevant knowledge snippets identified earlier to produce the final reasoned answer, A2.
And crucially, they mentioned external tools are prohibited during the synthesis process. Why is that?
They want to force the model to learn actual internal reasoning and deduction, not just learn to plug external results into a template. It's about simulating that authentic thinking process, building the capability to connect the dots internally, which is vital for complex tasks.
Okay, that covers FAS for generating scale offline. Now let's talk about HAS high-order action synthesis. This tackles a different, very real problem in agent training. What do you do with all the messy, suboptimal data?
Right. In typical SFT or RL, you often end up with tons of trajectories where the agent maybe took a wrong turn or wasn't perfectly efficient. This data is usually just discarded because giving accurate step-by-step reward signals for those intermediate steps is really hard and often risky. You might accidentally reinforce bad behavior.
Yeah, grading the entire trajectory as good or bad is easy, but grading step 5 out of 30 is tough.
Exactly. So the core insight of ACEs is to shift the focus. Instead of trying to make the model imitate only perfect trajectories, they focus on teaching stepwise decision-making by leveraging the choices available at each step, even within those imperfect runs.
Okay. Using suboptimal data to teach better decision-making. How does that work? Sounds a bit counterintuitive.
Think of it like reviewing game film, even from a game you lost. You look at specific plays. So for any given step in an existing trajectory, even a messy one, they use an LLM to generate, say, N alternative thought and action candidates for that specific step.
So at step 5, where the original agent did action X, the haste process generates other things the agent could have thought or done instead, maybe action Y or action Z.
Precisely. These alternatives could be better, worse, or just different valid approaches. They then merge the original step with these generated alternatives and shuffle them up.
So instead of just seeing the one action taken, the model is now presented with a menu of choices at that step.
Exactly. It transforms the single trajectory point into a decision space.
Okay.
And this leads to what they call contrastive decision action synthesis.
Contrastive, meaning it learns by comparing the options.
Right. The training data is formatted to simulate this. The model sees the options, then it simulates choosing one. Each time I will choose option 3. Then it sees the actual outcome or response that followed that choice in the original trajectory. And finally, a binary judgment. Was this choice ultimately helpful or not towards the final goal?
Wow, okay. That's really powerful. It's explicitly teaching the model to evaluate different paths at the decision point itself, using the context from trajectories that might have previously been thrown away.
Exactly. It extracts rich training signals from that underutilized data without relying on those tricky step-level reward numbers. It teaches the model why certain choices are better than others in context, which builds robustness and prevents overfitting to just one golden path.
Okay, so we have FAS generating massive scale offline, Hayes extracting value from messy data, and the two-stage CPT process with expanding context windows. This whole system sounds incredibly well thought out. Did it actually work? Let's talk results.
It definitely seems to have paid off. We already mentioned the big one, the 31.5% on HLE, Humanity's Last Exam. Cracking that 30-point mark for an open source model is a major milestone.
Absolutely. What else stood out?
Well, the 89.6% apart score on the Frames benchmark is also really telling. Frames is specifically designed to test if an agent can gather information from multiple perspectives and synthesize it into a consistent, comprehensive report. That high score suggests AgentFounder isn't just good at calling tools, it's excellent at reasoning about and integrating the information it gathers.
That points to deeper understanding, not just task completion. And what about the claim that CPT provides a robust foundation? Did they test that?
They did. They ran an ablation study where they took the AgentFounder 30B base model after CPT and compared it to the original Quinn base model without CPT. They fine-tuned both using 3 different standard SFT dataset configurations.
And the AgentFounder base model performed better regardless of the SFT method.
Consistently better, yes. Across all 3 SFT setups, the AgentFounder base achieved higher scores, with average gains of up to 6.45%.
Okay, that strongly suggests the CPT stage itself is providing a universally beneficial foundation. It's not just tuned for one specific downstream task. It makes the model fundamentally better at being an agent.
Exactly. It validates the whole premise, pre-align the foundation, and then specialize.
What about scaling? Does this CPT approach scale efficiently?
The scaling analysis was interesting. As you'd expect, performance generally increases with model size, going from their 1B parameter version up to the 30B, no surprise there. But the AgentFounder 30B model, with CPT, achieved an average accuracy of 48.9% across their benchmark set. This actually exceeded some larger baseline models trained without CPT, like DeepSeek v3.1, which apparently hit 43.4 on a similar evaluation.
So it's more parameter efficient. The CPT makes the model punch above its weight class, so to speak.
That's the implication, yes. Superior scaling efficiency. CPT helps the model leverage its parameters more effectively for agentic tasks rather than just relying on brute force scale.
And did they show CPT helps with the fine-tuning process itself? Like, does it make SFT easier?
Yes, the training loss curves confirm this. During the final SFT phase, all the AgentFounder models, which had undergone CPT, achieved significantly lower training loss compared to the baseline model that skipped CPT.
Meaning they learned the SFT task faster and more easily.
Right, it backs up the dual burden idea. Because CPT already handled teaching the foundational agentic skills, the SFT stage could converge faster and more effectively, focusing solely on aligning to the expert demonstrations. It alleviated that burden.
Okay, one last piece of evidence, the tool usage. Did the model just call tools randomly, or did it show some intelligence?
It showed clear adaptive behavior. On complex, open-ended tasks like HLE and the BrowseComp benchmark, the analysis showed a heavy-tailed distribution of tool calls. Lots of interactions, deep search is what you'd expect for research.
Okay, so it dug deep when needed.
But on more structured tasks like WebWalker or parts of GAIA, it showed a compact distribution. Fewer calls, more targeted usage. It was conservative when the problem didn't demand extensive exploration.
So it learned to calibrate its tool use based on the perceived complexity of the task.
Yeah, which is a really good sign. It's not just blindly following a fixed tool use script. It's making context-aware decisions about when and how much to rely on external information. That's a hallmark of a more intelligent agent.
Okay, so wrapping this all up, what's the big takeaway for you, for someone listening who's building or using LLM agents?
I think the main message from AgentFounder is that Agentic CPT isn't just some optional add-on or a minor tweak. It really positions itself as an essential architectural layer if you're serious about building specialized agents that need top-tier performance and efficiency.
We have to move beyond just trying to bolt on tool use capabilities during the final fine-tuning stage.
Exactly. This research strongly argues for pre-aligning the model's fundamental architecture for agency first. It enables leaps in both efficiency and capability downstream.
It really reframes the problem. But there was one final piece of data in their analysis that really caught my eye, relating tool use to accuracy.
Yeah, the correlation between the number of calls and performance.
They found the sweet spot. The highest accuracy, 81.3%, came when the model used between 1 and 8 tool calls per task.
Right. But interestingly, accuracy dropped quite a bit, down to 66.7%, when the agent used 0 tools.
Which suggests, even for this advanced AgentFounder model, there's still a significant reliance on external information retrieval, even for potentially simpler queries.
It does. And that leads to a really interesting provocative thought for you, the listener, to mull over.
We saw AgentFounder demonstrated pretty remarkable robustness handling long, complex tasks. It still maintains 17.5% accuracy, even when making over 40 tool calls. So it can handle complexity.
So the question becomes, how much further can this continual pre-training methodology, maybe with even better FAS and haste data, be pushed to build more internal agentic intelligence?
Could we reach a point where the agent can reliably solve more of these lower complexity tasks, the ones needing 1 to 8 calls now or even 0 calls, without resorting to external tools, instead leveraging its own pre-aligned internal knowledge and reasoning skills developed during CPT?
That ability to confidently choose not to search because it already knows or can do the answer reliably and instantly, that feels like the next frontier. Pushing CPT to enable more tool-free, instantaneous inference for a wider range of problems, that might be where the next big performance leap for agents lies. Something to think about.